Swayam Prabha. Digital India. Educated India.
So, in the last lecture, if you remember, we started the Fourier integral representation, where the last two equations we derived, equation 8 and equation 9. Let us see the equation 8 first, just for recapitulation. Your equation 8 is f x equals 2 by pi 0 to infinity f t into cos of alpha t dt, cos of alpha t dt into cos of alpha x into d alpha. This was your equation 8. So, in this equation 8, if you set f of alpha, capital F of alpha equals root over 2 by pi 0 to infinity f t into cos of alpha t dt. If we substitute this one, say this will be equation 10. This f alpha equals, we are setting capital F alpha equals root over 2 by pi 0 to infinity f t cos of alpha t dt. Then your f x you can write down as 2 by pi 0 to infinity f of alpha into cos of alpha x d alpha. Just this 0 to infinity f t cos alpha t, this you are writing as f of alpha. So, f x will be root over 2 by pi, since f alpha we have taken root over 2 by pi. So, f alpha is this thing into cos of alpha x into this one. This is equation 11. Now, please note that this f of capital F of alpha is called the Fourier cosine transform. Fourier cosine transform of f x. So, now actually from these representations we are defining what is Fourier cosine transform. Please note this one. If I have a function f x which is defined in 0 to infinity, then the Fourier cosine transform of f x can be represented by the equation 10, and this we defining at f of alpha equals root over 2 by pi 0 to infinity f t into cos of alpha t dt and this one. So, if in this equation 11, if you consider in this equation 11, suppose f alpha is given, suppose this value of f alpha is given to me and f t is unknown function. Please note that in this 11, if f alpha, sorry, not this, in this 11, if this f alpha is known to me and this f t is known, then it is an integral equation of the function f t, it is an integral equation of the function f t, and formula 11 gives the solution of that equation. So, please note that f alpha we call it as the Fourier cosine transform of the function f x, and from here if I know f alpha, then I can represent it in terms of f x also. Similarly, if you consider the equation 9, if you recall, I am just writing again, equation 9 is your 2 by pi 0 to infinity f t into sine of alpha t dt into sine of alpha x d alpha. This is your equation 9. We can write the following equations from here. Say phi of alpha, this is equals root over 2 by pi 0 to infinity f t into sine of alpha t dt. We are setting this integral equals to phi of alpha, which will be a function of alpha after integrating with respect to t. So, we are telling phi of alpha is this actually will be equation 12, and in that case your f x will be root over 2 by pi 0 to infinity phi of alpha into sine of alpha x d alpha. Say this will be equation 13. Therefore, in this case this phi of alpha, this is known as Fourier sine transform. We call it as the Fourier sine transform of the function f x. So, I hope it is clear now that if the function from here a function f x is there, then the Fourier sine transform of the function will be psi of alpha, which is nothing but root over 2 by pi 0 to infinity f t into sine alpha t dt. So, just let me go back to the slides and tell you this one. So, in the equation 8 what you are doing, equation 8 was this one, f x equals 2 by pi 0 to infinity f t into cos of alpha t dt into cos of alpha x d alpha. On this equation, if I put set f alpha equals root over 2 by pi 0 to infinity f t into cos alpha t dt, then 8 takes the form f x equals root over 2 by pi 0 to infinity f alpha into cos of alpha x dx, and this we call it as the f alpha, that is this capital F alpha defined by 10, we call it as the Fourier cosine transform of the function f x. So, that the kernel is nothing but cos of alpha t, and whenever capital F alpha is known to me, by evaluating the integral I can find out what is the corresponding function, that is f x also I can evaluate. This only we have told. In 11, if we assume that f alpha is given and f t is unknown function, then by evaluating the integral we can find out the value of f t. And on the same way, formula 11 gives the solution of that, and on the basis of 9, means your this equation f x equals 2 by pi 0 to infinity f t sine of alpha t dt into sine of alpha x d alpha. Using this equation I can obtain this. If I assume that phi alpha equals root over 2 by pi 0 to infinity f t into sine of alpha t dt, and I can write down f x equals root over 2 by pi 0 to infinity phi alpha into sine of alpha x into d alpha, and this again we call it this phi alpha we call it as the Fourier sine transform of the function f x. So, we till now we define two things, what is the Fourier sine transform, what is the Fourier cosine transform. For sine transform the kernel is sine of alpha t, whereas for cosine transform the kernel here becomes cos of alpha t, just like for Laplace it was e power I alpha x. Next we want to study the Fourier integral representation in the complex form. So, Fourier integral representation of the function f x you can write down like this. Your f x is 1 by pi 0 to infinity. So, earlier it was 0 to infinity, now it becomes minus infinity to infinity f t into cos of alpha into t minus x into dt into d alpha c. So, Fourier integral representation of the function f x is like this: 1 by pi 0 to infinity minus infinity to infinity f t into cos of alpha into t minus x dt into d alpha. This again we can write it in this particular form: 1 by twice pi into minus infinity to infinity minus infinity to infinity f t into cos of alpha into t minus x into dt into d alpha. We can write down this thing because your cos of alpha into cos of alpha into t minus x is even function of alpha. Since cos of alpha into t minus x is an even function of alpha, therefore, this 0 to infinity I can write it using the property of definite integral minus infinity to infinity, and that is the reason we have divided by 2. So, I had the original representation of f x as this, and since cos of alpha into t minus x is an even function, therefore, this 0 to infinity can be replaced by minus infinity to infinity, and 2 will be divided over here. Again, you know this thing, sine of alpha into t minus x is odd. This is an odd function of alpha. So, since this is an odd function of alpha, so I can write down the equation as 1 by 2 pi. The earlier equation whatever we wrote, that is equation 2 actually, and this we can write down 1 by twice pi minus infinity to infinity again f t into sine of alpha into t minus x into dt into d alpha. This will be say equation 3. Since this is an odd function, therefore, the value always will be 0. So, you multiply now 3 into basically minus I and add with 2. Basically, on this you multiply it by minus I and the equation 2, the last equation whatever we wrote, add this equation. If I am adding this, then basically I have sin alpha into t minus x, and there I have cos alpha into t minus x. So, these two together, this will be 1 by twice pi minus infinity to infinity f t into e power minus I alpha into t minus x into dt into d alpha. So, it is equation 4. This e power minus I alpha into t minus x I am getting from this cos of alpha into, I will get a term of this, I have not written cos of alpha into t minus x plus I into sine of alpha into t minus x, and by representing this one, and we are getting this one, and this we call as the, this equation 4 we call as complex form of FIR, Fourier integral representation. This is the complex form of the Fourier integration, complex form of this one, and this we can write down complex form of Fourier integral representation. That is, your f x can be written in this form 1 by twice pi minus infinity to infinity, again minus infinity to infinity f t into e power I alpha into x minus t, I can write down I x minus t into dt into d alpha. This is say equation 5, and which is again in that case you will obtain the equation 5. So, if I choose 5, say I am choosing the equation 5 here. If I choose 5, that is your f x, again I can write down like this way, 1 by root over twice pi into minus infinity to infinity e power I alpha x into, I am just breaking it, e power I alpha x, I am bringing it out because it is not independent of t. So, 1 by root over twice pi minus infinity to infinity f t into e power minus I alpha t dt into d alpha. This is your equation 6. So, I have chosen not equation 4, but equation 5, which is the another form, then I am writing it like this. In this equation 6, say we are denoting this thing f x, f of capital F of alpha equals 1 by root 2 pi minus infinity to infinity f t into e power minus I alpha t dt. If I choose f alpha equals this integral, inside integral basically 1 by root 2 pi minus infinity to infinity f t into e power minus I alpha t dt, which say this is equation 7, then I can write down my f x as 1 by root over twice pi minus infinity to infinity f of alpha into e power I alpha, x will come, this e power I alpha x is here, e power I alpha x into d alpha. Please note this thing, that integral 6 and integral 7. So, if this integral 7 exists, then we call it as the Fourier transform of the function f x, where the kernel we are assuming as e power minus I alpha t. So, sorry, this will be equation 8. This is equation 8, and this equation, if it exists, if this integral exists, then this integral f alpha equals 1 by root 2 pi minus infinity to infinity f t into e power minus I alpha t dt. This one we call as Fourier transform. This we call as Fourier transform of the function f t, and here your kernel obviously is e power minus I alpha t. So, please note this one, that this equation 7, that is f alpha equals 1 by root 2 pi minus infinity to infinity f t into e power minus I alpha t dt is known as Fourier transform of the function f t, where the kernel is e power minus I alpha t, and we represent it like this: Fourier transform of f t, this is equals to f of alpha, and which is nothing but 1 by root 2 pi minus infinity to infinity f t into e power minus I alpha t into dt. So, if capital F alpha exists, then equation 8, if you see, where we have defined f x equals the integral, this is known as the inverse Fourier transform of f alpha. So, from 8, if I know f alpha, I can tell what is the value of f x. So, equation 8 known as the inverse Fourier transform of f x, and which we write as f x equals Fourier inverse of f of alpha, and this is equals to 1 by root 2 pi minus infinity to infinity f alpha into e power I alpha x into d alpha. So, this is say equation 10. So, basically your Fourier transform of f t is given by equation 9, and inverse Fourier transform of this one we call it inverse Fourier transform we can obtain from equation 10. Let us just see quickly here. Fourier integral representation of the function f x is this one, as we have done it earlier, f of t into cos of alpha into t minus x, which can be written as minus infinity to infinity, 0 to infinity can be represented by minus infinity to infinity, because cos of alpha into t minus x is an even function. From the properties of definite integral we can tell this, and also we know sine of alpha into t minus x is odd function. So, that value of this indefinite integral will be 0. Now, multiply equation 3 by minus I, and if we add with the equation 2, I will obtain in e power form basically, because you have the cos of alpha into t minus x and sine of alpha into t minus x, and from here you can get this equation 4. This equation 4 we call it as the complex form of the Fourier integral representation. Please note this one, this equation 4, because we will use it again afterwards. So, once I am getting this, so f x equals 1 by twice pi minus infinity to infinity minus infinity to infinity f t e power I alpha into x minus t dt into d alpha. This e power I alpha x I can bring outside the dt because alpha is independent. So, that I can write down the equation 6 as I told. Now, in 6 we are denoting f alpha, capital F alpha equals 1 by root 2 pi minus infinity to infinity f t into e power minus I alpha t. In that case, you can write down f x equals 1 by root 2 pi minus infinity to infinity f alpha into e power I alpha x. Equation 7 basically known as the Fourier transform of the function f t, whereas equation 8 tells us the inverse Fourier transform of the function capital F of alpha. So, basically if I know the function f x, I can find out the Fourier transform of the function from equation 7, whereas if I know the Fourier transform of a function, that is f alpha, corresponding function or the inverse I can obtain from equation 8. Now, if this integral exists, is known as the Fourier transform of the function, which we are denoting as equation 9 basically now, same thing we are saying. And if the Fourier transform exists, then value of f x can be obtained from this. So, equation 9 and 10 gives me these two forms over there. So, please note this thing, that this equation 9 and 10, these two will be giving me the Fourier transform of the function as well as the inverse Fourier transform of the function f of x. Now, I told you about the equation 4, the equation 4 which I got the Fourier integral representation of the complex form. In 4, if we put in equation 4, if we put alpha equals minus omega say, in that case your f x will be equals to 1 by twice pi minus infinity to infinity. This will be actually minus omega. So, the limit will be changing here, that is plus infinity to minus infinity it will be. This one is minus infinity to infinity f t into e power I omega into t minus x into d t into minus d omega. So, that this minus, if I change it again, 1 by twice pi, this will be now minus infinity to infinity minus infinity to infinity f t into e power minus I omega into, I can make it x minus t into d t into d omega. And this equals, you can write down 1 by twice pi minus infinity to infinity, this minus infinity to infinity f t into e power minus I alpha into x minus t into d t into d alpha. Simply I am replacing omega by alpha, nothing else I am doing. So, this equation is 4a. In the case, so earlier I used equation 4 and I obtained equation 9 and 10, which are the Fourier transform of the function f x and the inverse Fourier transform of the function capital F alpha. Now, in 4, if I use alpha equals minus omega, then f x I am writing like this, 1 by twice pi minus infinity to infinity f t into e power minus I alpha into x minus t into d t into d alpha. So, instead of 4, if I consider 4a, means if I work with now equation 4a, then I will get the some other form. Then f x equals 1 by root 2 pi, again you can represent same way, e power minus I alpha x 1 by root 2 pi into minus infinity to infinity f t into e power I alpha t into dt into d alpha. This is say equation 11. So, now you denote here capital F of alpha equals 1 by root 2 pi minus infinity to infinity f t into e power I alpha t dt. This is say equation 12. Then f x can be written as 1 by root 2 pi minus infinity to infinity f alpha into e power minus I alpha x into d alpha. So, if I change in this particular form, then also equation 12 is known as the Fourier transform of the function f x, whereas inverse Fourier transform of f alpha can be obtained, this will be capital F alpha, can be obtained from equation 13. So, effectively if you see equation 9, 10 can be used to find out the Fourier transform and inverse Fourier transform of the function, and for 12, 13 also let me just write it again. Fourier transform of f t, this is equals to f of alpha, and this is nothing but 1 by root 2 pi minus infinity to infinity f t into e power I alpha t dt. This is equation 14, and if I use this, then Fourier inverse of the function of f of alpha, this is equals f of x, say this equals, I can write down 1 by root 2 pi minus infinity to infinity f of alpha into e power minus I alpha x into d alpha, which is equation 15. So, therefore, what we are observing, if you think about, if you see the equation 9 and 10 or 11, 9 and 10, there the change was only e power minus I alpha t was here, and in this case this was replaced by e power plus I alpha x. So, in both cases you will get the Fourier transform, and please note that in the books somewhere they have used the kernel as e power minus I alpha t, somewhere they have used the e power I alpha t. So, anyone can be used as an kernel, either e power I alpha t or e power minus I alpha t, and I can obtain the Fourier transform of the function accordingly either from equation 9 and 10 by getting the Fourier transform and inverse Fourier transform, or I can use the equation 14 and 15 also to find out the Fourier transform and corresponding inverse Fourier transform. So, in the next classes we will see, next lecture we will see that how to find out the Fourier transform of some function. Thank you.